Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Jonas B with us today. Hey, Jonas.
Hey, Frank. Hey, everyone.
What's your geolocation, Jonas?
So right now I'm in Vilnius, Lithuania. I'm in my wonderful apartment where I've been in for like months now due to COVID mostly.
I think you have the pleasure of being the first Lithuanian author on this series.
Really?
Very cool.
That's cool.
And I see some musical instruments over your left shoulder there. Do you play those?
Yeah, those are my guitars. I'm not sure if you can see them. Maybe you can see them
Very
like
cool.
this. I used to play them, but that's before my doctoral studies. Then that took over and I kind of stopped all of a sudden. I'm planning to go back into it. I
Cool.
really like playing guitar, but not sure when that's going to be.
What do you like to play?
Mostly rock, metal sort of stuff.
Sure.
Nothing too interesting. I'm not too good at it, but it's still something fun.
It's
a
fun.
hobby.
One has to have hobbies these days, especially when one is bunkered down for months and months.
Oh man.
And still looking like it's going to be months. So yeah.
Yes, especially here. It's been like, I think we were the worst in Europe per capita at one point, or maybe one of the worst.
Yeah.
So the last month in particular was really harsh.
Yeah. Yeah. We're not doing so well in the US either, although we have a vaccine. I have not heard any plans on when I might get it. So it's going to be a while.
Yeah, same here.
Yeah. So Jonas, what do you like to do for research?
Well, I'm mostly a computer science guy. I ended up in like astrophysics sort of by accident. I finished my master's in like computer science and then got offered this PhD position to study star clusters. So that's where I ended up with. And basically what I do is apply convolutional neural networks to various things to do with star clusters. So like my passion is artificial intelligence and neural networks in particular. But I happen to be in this sort of specialty right now.
Cool. Very cool. Yeah, I know a number of computer scientists who are active in astronomy. So, and that is going to bring us to this really lovely article. And there we go. And speaking of your computer science background, we have the study of star clusters in the M83 galaxies with a convolutional neural network. And Jonas, take us away.
So yeah, this paper is kind of complicated because it's actually sort of a third in a series of works where we explored the application of convolutional neural networks to star cluster analysis. And well, to be brief, basically what we did in our previous publications is figure out how to use convolutional neural networks to derive age, mass, size, and extinction of star clusters.
Okay.
And we did that for clusters of, well, several different galaxies. So like the meat of like the convolutional neural network part is in those papers, but like really briefly, I'd like to explain why use convolutional neural networks at all.
Okay.
Because all of these parameters I mentioned have been derived in different methods before. It's nothing like super novel. And well, basically the way I see it is that these convolutional neural networks, or CNNs for short, provide like a really consistent joint pipeline for analyzing star clusters through various lenses. And like the main upside is that there's no fitting, no Markov chains, nothing like super computationally intensive like that. You don't get cluster size one way and ages in some completely different manner. It's all integrated, all joined. You just input an image and get everything you want to know about the cluster on the other end.
Cool.
And you know that the network was like trained to derive all of those parameters from the same data in the same manner. So that's basically my sales pitch for why use CNNs here. So I'm not going.
So you train this particular network on M83 as well?
Yeah, this is trained for M83 clusters in particular. previously we worked with M83 and Andromeda.
Okay.
So in Andromeda, you get like these more resolved clusters because it's like, the galaxy is way closer, and M83 is much further away. And it's also, well, in this paper, at least we're using data from the Hubble Space Telescope. We also used the Hubble Space Telescope data for Andromeda, so it's a like similar sort of system. So you get way less resolved clusters in this galaxy, and they're way more massive on average as well.
Okay, cool.
Yeah. So basically, to sum up, I guess, this particular paper is that we take the convolutional neural network we already like trained to derive all of these parameters, age, mass, extinction, size, etc. And we perform cluster search on M83 with it, and sort of look at various cool things that you can see in the clusters in this galaxy.
Nice.
So yeah, we can probably move to figure 1 immediately.
Yeah, let's take a look at
It's like on page 2, I think.
AJ. Okay.
So basically, figure 1 is here because it looks really cool. That's its main purpose. But what it
does
shows,
look very cool.
see,
It does look
my co-author insisted that it has to be in the paper, so we put it in the paper.
It's a good one.
So basically, what it shows is the M83 galaxy, and you can see what it looks like, sort of. Because it's covered with these mock clusters, these artificial clusters that we drew on the galaxy.
Ah, got it.
Yeah, and what this image is used for is for testing the neural network.
Right.
Like the first half of the paper is going to be just about testing the network because, well, turns out in astronomy, it's kind of difficult to show if your method is performing well, especially when it comes to search. This may not be surprising to like physicists listening, but like I said, I'm from a computer science background, and it's way easier there, especially in like when machine learning is concerned, where you always have a test set of some sort, and you just test it and you're done. This is way more involved. So we can actually, I can go through some of the parameters that we derive here because I mentioned only 4 and we do a bit more than that. And we can actually see everything in the table on the bottom of the page here. So in the first 4 rows, you see the ones I mentioned, that is age, mass, extinction, and size. And like on the 3rd column, you can see their ranges, which is like not too important right now, but it's a good thing to know if you're reading the paper. Yeah, so these are like the 3 main parameters that we derive for star clusters, and they're all a little bit different. Like, so if we move to the next pair of lines, metallicity and distance are basically fixed. We don't do anything with it. We just took those values from some papers, and we're leaving those as constants.
Okay.
And one of the more like interesting things that are listed in the 3rd pair of rows, I guess, where it says inferred. And this is visibility and cluster or background. So these 2 things are also what the neural network outputs for each image that we give it.
Okay.
So cluster or background is basically how likely the network thinks that a specific image contains a cluster. So it gives you a 1 if it thinks that a cluster is likely to be in an image, and a 0 if it thinks that the image is likely just a background.
Okay.
So this is like the main key point for performing cluster search. And that there's an additional parameter that we call visibility, which is basically just a proxy for signal to noise.
Right.
And its job is to tell us what the network thinks, how clearly the cluster is seen in an image, in the network's opinion. So basically, the larger the number, the more bright the cluster relative to its background is. Excuse me.
Good.
So I wish I could show you some figures from a previous paper, but I can't because it's explained better there. So we'll just have to move on and see some results from this paper, I guess. So if you could move to figure 2.
Figure 2.
Yeah. So in figure 1, we've seen all of these artificial clusters superimposed on a background of M83. And this figure actually shows the results after you perform the search. So these are the 2 parameters I just mentioned. On the x-axis, you have the cluster or background classification parameter. I'll just call it class CB for short. And on the y-axis, you have visibility. So you go to the right, it's more likely to be a cluster. You go up, it's more clearly a cluster, that sort of thing. Okay. And these are on the right, like this histogram on the very right. It's a histogram of visibility. It's just marginalized over class CB. And on the top is the same for class CB, just a histogram of class CB marginalized over visibility. And basically, the idea was to show where it puts real clusters and backgrounds compared to each other. So the sort of a gray, this gray histogram in the background and these gray points as well are cutouts of backgrounds of M83, while the blue outline are mock clusters that were inserted into the image. So you see most of these like blue dots are concentrated on like high class CB, high visibility, which is exactly what we want. Right. But it's not perfect. You do have to note that some of the mock clusters are like really faint. And if you put them in a dense background, if you hit some huge blue association in a galaxy, you're basically unable to find it. And also, some of these gray points contain real clusters because we basically can't filter those out. If we take a background from a galaxy, we always have a chance to hit like a real cluster. So usually in machine learning, what you do, you draw some sort of like sensitivity recall curve. You pick the number of false positives you're willing to tolerate, some trade-off with false negatives, just pick a spot and you go with that. Here, you can't do that because all of the true negatives are not really true negatives. They always have some noise. So the best we can do here is pick some thresholds for these 2 parameters by eye. And this is what was done in this paper. You can see these, these red dashed and dotted lines. So the dashed lines is our final version, what we went with. This is basically targeting some recall or completeness percentage and looking by eye how good it looks, how many like false positives it has and stuff like that. So the next figure.
And the dotted red lines, that is some band about the chosen value?
Well, these are actually just some alternatives that we looked at just to illustrate the differences, and they're visualized a bit later. Yeah, you can see those dotted lines like actual clusters that you get if you take one dotted line. If you take a dashed line, took the other line, this is what you get, sort of thing.
Got it.
So you'll see that a bit later.
Okay, thanks.
Yeah.
Cool.
So figure 3 will be just analyzing these mock clusters after they've been filtered by these dashed red lines.
Okay.
So there's a whole bunch of stuff that you can see here. I think I'll just go through like the main takeaways. So on the left is probably the figure that's the most clear. It's basically just a spatial map of the galaxy. And each little square is the recall or completeness value that you get in that spot. And the spiral arms of the galaxy are outlined in this very, very faint white outline.
Yeah.
So overall, the completeness is about 80% here, but you get slightly lower completeness on the spiral arms, which is, well, expected because the background is really dense on the spiral arms. So you expect the clusters to get hidden better.
Yeah.
While the 6 figures on the right are basically the same, just not spatially, but by various combinations of parameters. So for example, if you look at figure B, that has age on the x-axis and mass on the y-axis. And again, depending on where the cluster is on those two axes, what sort of a completeness percentage you get. And it really clearly drops down from almost 100% to a 0 as you get to lighter and older clusters.
Right.
Right. Yeah. This is like the most obvious thing from all of these figures, but that's again sort of expected because smaller lighter clusters just have less stars in them. They're harder to find. And older clusters are really like faint red things that are hard to find. So that's nothing too out of the ordinary. And on the top, you see the figure for the spiral arms. We call this the inner region, but just imagine that it's the region on the spiral arms. And on the bottom row, you have the same thing just for the outer regions. But the differences between those are not too large. It's just slightly worse on the spiral arms, so I'm not going to talk too much about the differences. So if you look at D and E, for example, you can see a similar effect as well, just not as pronounced. This is age on the x-axis and extinction, which is behind how much dust a cluster is hidden behind, basically. And as you get more extinct and older clusters, you find slightly less of them. This is pretty intuitive. And there's like this black hole in the upper right, but it's there just because we don't have any mock clusters that are that extinct and that old, because they're basically invisible at that point. You can't find them using any method. So that's more of an artifact of the experiments and not like a real recall rate.
Okay.
I'm with you. And finally, F and G is kind of a similar situation. It's just mass on the X and extinction on the Y-axis. And there's a slight gradient going to the upper left corner where the higher extinction and lower masses are, but it's, again, not too pronounced. So overall, the network performs pretty well. There are some artifacts, but they're nothing you wouldn't expect, basically.
Okay.
So we can move to the next one, I think. Don't really remember what the next one is. So let's.
These are detected cluster candidates.
Oh, yeah. So at this point, we're moving away from the mock clusters. We're done with testing. And we're actually looking for real cluster candidates. We're calling all over the paper these things we're calling cluster candidates because you need a whole lot more verification to make sure that they are real clusters. And this is not something we do in this paper.
Right.
Yeah. So on the upper row, you see clusters superimposed, marked as dots superimposed on the image of M83, and they're colored by age. So blue is young clusters and red is old clusters. And the three panels A, B, and C are the three different lines that you saw earlier for visibility cutoffs.
Okay.
So if you cut off visibility a little bit lower, you get these 4,680 clusters on the very left. If you get it much higher, cut it much higher, you get what's seen in panel C.
Right.
Right. And the final version that we used everywhere is panel B.
Right.
So there are not a lot of insights you can get from this. Basically, panel B is what looked best to us, like judging all of those things by eye. But these are just for show, for how much it could differ just by varying that parameter a little bit. So for example, on A, you can see much more older clusters all over the place. While on panel C, there are still a lot of young clusters, but much less old clusters, just because old clusters are, well, much harder to find usually. So two more interesting things, in panels D, E, and F, you can see this exact same clusters that you saw in panel B, only they're subdivided into categories by their age. So on the left in panel D, you get young clusters. In panel E, those are sort of middle-aged clusters, and F are old clusters. Like I said, this is the same that you see in panel B, but if you separate them out into groups, it's kind of much easier to see how they're distributed. So for example, young clusters on the left, they're really bunched up around these star formation zones, spiral arms, or places like that where there's a lot of gas. And on the right, the old clusters are much more evenly distributed. Which is exactly what you'd expect. They're already like mixed around the galaxy. So I guess we'll, sorry, go ahead.
Let me just ask, so did this analysis find a lot of what were previously unknown clusters?
Well, yeah, there are a few catalogs for M83 of star clusters. None of them really like claim to be like super complete.
Right.
So it's not like we're trying to do something much better than everyone else, because nobody just compiled like a full catalog. Usually what people do is filter out only like super confident clusters in some region, or maybe sometimes the whole galaxy, but you don't get a large number like that, especially if it's like human picked.
Right.
So we find much more cluster candidates than the catalogs that we know of. And there are obviously a lot of new ones here. So sort of, yeah, but with some caveats.
Understood. Yep.
Right. So these distributions we're going to analyze in more detail a bit later. We can scroll on.
Okay.
PDF reader is not cooperating today.
Yeah, well, we've got a little bit of a bandwidth lag probably too between here and Lithuania.
That's possible. And but Zoom routes through China anyway. It should be the same for everything. Anyway, this figure is actually really involved, and it's best viewed in comparison to either our older papers or to papers from other authors, but it's not an option right now. So I'll just highlight like a key thing that you should look at. Basically, all of these figures are just all of the cluster candidates that we found, and comparing them through various parameters. So for example, in panel A on the top left there, you get age on the x-axis, mass on the y-axis, and all of the cluster candidates just marked off as dots. On panel D, you get mass on the x-axis and extinction on the y-axis. All of the clusters are marked, and they're also colored by age here, starting from like blue for very young ones and red for older ones.
Okay.
So not to get in too much detail, I guess one of the more interesting things to look at is, for example, if you look at panel A, and usually when you classify backgrounds in a galaxy, like images that are not star clusters, you get a lot of these backgrounds classified as small mass and like mid-aged or old age objects. So yeah, about that area going to the right.
Yeah.
Because the neural network has no concept of a cluster, right? It doesn't really care what image you pass to it. It can give those like parameters that I mentioned earlier, like class B or visibility, which gives you a hint about what it thinks, but it still gives out mass, it still gives out age. And even if you pass it the background, you still get an age, you still get a mass, and etc.
Right.
So if you pass images of backgrounds through it, you get a lot of these small mass, mid-aged clusters, as I mentioned. And there are not a large concentration of these sort of objects here, which kind of supports our search procedure, that it is not picking up backgrounds, but it's actually picking up real clusters. A similar thing can be seen in panel B, where a lot of backgrounds would line up in this kind of diagonal between extinction and age, but there are barely any clusters in the diagonal here. Well, the diagonal for the backgrounds would be like much higher. So unfortunately, you'll have to take my word on all of this. But if anyone's curious, then they can see our previous paper where there's charts for all of those things. Cool. So yeah, the main kind of the weird thing in this is like the large concentration of young clusters with a low mass. So you can probably most clearly see them in panel D, like on the right. Mm-hmm. Well, yeah, you can see them everywhere if you look hard enough, but they're colored in panel D. So you get a lot of these blue dots on the left of the chart, right? And these are where the young and not massive clusters bunch up.
Right. Yep.
So yeah, these are the objects that are usually missing from catalogs because they're like really difficult to find. Well, they're not exactly difficult to find. You can see a whole lot of objects like this in a galaxy, but it's really hard to tell what's a cluster and what's not.
Right.
Because on like these bright star forming regions, you get a lot of blue stars and they're like these huge associations, and you can't really tell what's gravitationally connected there or not. But our network still picks up objects like those.
Cool.
And if we move to the next figure,
okay,
we explored that a little bit there. Yeah, so figure 6. I guess the most interesting part is panel A. You have here cluster mass on the x-axis and their counts on the y-axis, basically just mass histograms. Mm-hmm. So these lines, there's like a solid line in the middle, and there's a dashed line on the bottom and a dotted line on top, are Schechter mass functions, basically what masses you'd expect to see in a real cluster sample, with different truncation levels. So the lines are wiggle a little bit near larger, higher masses. Yep. And the faint histogram in the background is all of our clusters. That's, of course, affected by all sorts of selection effects. So what you usually do when looking at these masses is take a sample of a little bit of younger clusters, because there are a lot of selection effects for older clusters. And younger clusters here are marked with these really large gray circles. Yes. And as you can see, the Schechter mass functions fit them pretty well, which is also kind of tells us that we're not too far off from real cluster samples. And what you usually get in other catalogs is the sort of a turnoff on the very left. There's a very small number of like really low mass clusters compared to what you'd expect. And we don't get that because our network picks up a lot of that. Okay. And of course, a lot of that could be junk, but well, in this work, we decided to just go with what the network picks, because in the usual catalog construction, it's the human who gets to choose last. And here we wanted a sort of an alternative with its own biases, of course, but humans also have biases in this regard. Yep. So in order to not take too long, I suggest just skipping B and C, because those are like minute details, and moving on to my favorite figures in this.
All right, favorite figures, always good. Okay, 7 and 8.
Yeah, 7 and 8. And this is a part.
Ooh.
I'll have to ask you to do a lot of work, Frank, because we'll be moving between figure 7 and figure 9 a whole bunch.
That's fine. That's fine.
So yeah, these are basically, let's look at figure 7 first. These are basically histograms of clusters against the cluster distance from the spiral arm. So in order to explain real quick what that is, you scroll to figure 9. So yeah, let's just look at panel A for now. This is again a bunch of clusters. Well, the cluster candidates that the neural network found superimposed on the galaxy. And cluster A basically just visualizes how we calculated distances from a spiral arm.
Yes.
So the black outline are the dust lanes of a spiral arm, which is just like a stable point you can choose to start your count because it's really easy to trace. And the colors represent distances. So you get positive distances in the red side. So this is in front of the arms, clusters that are leaving the spiral arm. And the blue colors are negative distances. And those are clusters that are trailing the spiral arms.
Okay, so this is it's an orientated curve.
Yeah, the distances, different distances are denoted to different sides.
Correct. I'm with you.
We can, before moving back, we can look at panel C as well. And panel C is our cluster sample with some of the lowest mass clusters thrown away, just for clarity. And here we're looking at values of extinction. So blue dots are clusters that have very low extinction, and red dots are clusters that have very high extinction.
Okay.
Yeah, and you can already kind of see that there are a lot of red dots around places where there's a lot of dust. So spiral arms and stuff like that, center of the galaxy. Now, if you go back to figure 7, I'd like to show you the same thing there. So again, we're looking at panel B this time. And again, distances from the spiral arm are on the x-axis. And on the y-axis, we have counts of clusters. And in panel B, they're grouped into 2 categories. Basically, blue means clusters with low extinction, and red means clusters with high extinction. That is a lot of dust in front of them. Yep. And you see this little pretty clear peak right on 0 where the spiral arms are of clusters with high extinction.
Yep.
And well, that makes a lot of sense because they're right on the spiral arms. There's a lot of dust. There are more clusters that have high extinction. Now, this in itself isn't too interesting. The reason I'm showing you this is just to get an intuition on how to look at these figures.
Yes.
So more interesting finding, and it's one of the our main findings, is in panel A. This is the same thing, distances from the arm on X, counts on Y. We have 3 categories here. So the blue line are young clusters,
yes,
about 10 million years and less of age. The yellow line are like these slightly older clusters, and the red curve is very old clusters. So unfortunately, there are a whole bunch of like selection effects with the distances here. So you can't look at anything below like negative 500 parsec and positive 1 kiloparsec. So there's kind of a narrow range in the middle there where the results are like actually reliable. Okay. But if you look at that range and at the red curve, you can see that it's really very uniform there.
Yeah.
It's like that means the clusters are well distributed uniformly, no matter their distance from the spiral arm. And this is kind of what we'd expect because we're looking at clusters that are 100 million years and older. And these already have traveled about at least 1 orbit around the center of the galaxy, and they're pretty well mixed around the galaxy. So you'd expect them to be uniformly distributed. And this is actually what we saw when we looked at the charts previously in like figure 5 or so.
Yes.
A very similar thing. Now for the interesting stuff, looking at the blue line, you can see the sort of a peak at around 400 parsec, like the first bigger one, right? And for the yellow curve, you can see a peak at around 700 parsec. Well, it's very approximate, but it's there. And this result is pretty robust because we repeated it with various setups and still got the same result.
Mm-hmm.
And what's really interesting that basically maybe some background on spiral arm density theory. Basically, what you'd expect looking at a spiral out of a galaxy is for clusters up to some distance. Clusters to be born on a spiral arm somewhere where there's a lot of gas, and for them to move out of it and be in front of the arms. And the older the cluster is, the further it is from the arm. So basically, distance should be correlated with age for younger clusters, at least.
Nice.
Clearly.
Very clear.
So if you take the speed at which the spiral pattern itself rotates, which has the same angular velocity no matter the distance from the center, and you take the angular velocities at which objects, including star clusters, rotate around the center, which is slightly different depending on the distance, you'd get these exact peaks that clusters that are about 10 million years or a bit younger should be around 400 parsec in front of the arms. And clusters that are like 50 million years or so should be about 700 parsec in front. So this is like one of our main findings.
Nice.
It sits really well with the density wave theory, so we're happy about that. Okay.
Cool.
Panel C is not that interesting, so I think we should skip it. Let's move to figure 8, because that deals with density, and that's also kind of interesting. So this is kind of similar. You have distances on the x-axis, but this time the distances are from the galactic center.
Yeah. Okay.
And on the y-axis, it's not a histogram anymore. On the y-axis, you get just a value of a specific parameter.
Okay.
So in panel A, you get density, which is basically how, on average, close the stars in the cluster are to each other. On panel B, you have mass, and on panel C, you have their size, which is the spatial extent of a cluster. Right?
Yes.
And density is basically just calculated from mass and size. So these are panels B and C are components of A. So I'll mostly just talk about A.
Okay.
And the clusters are here plotted out as points, and they're colored with their age. So again, blue is young clusters, red is old clusters. Right? And there are two lines here that I'd like you to look at. The blue line are like a group of younger clusters and their average density as a function of their distance from the center of the galaxy.
Yeah. About 2.
Yeah.
Okay.
And the red curve is the same just for older clusters.
Yes.
Yeah. And what's interesting here is that from distances like 3 parsec and up, the densities of these two groups are pretty similar. They're like definitely within error bounds. They're almost the same. But as you get closer to the center of the galaxy, the older clusters get more dense on average than the younger clusters.
Yep.
And also that makes a lot of sense, because the closer you get to the center of the galaxy, the denser an environment you have. So the easier these clusters are disrupted and like ripped apart. So in order to get to an old age in a place like this, you need to be dense. Otherwise, you're just going to be ripped apart by various forces.
Yep.
So yeah, that's like one of the main things we found that's also very interesting. Well, like I mentioned, on panels B and C is basically just components of those. So for example, on B, you have mass, and you can see that the mass of older clusters like goes up slightly towards the center.
Yep.
And on C, you have like spatial extent, size, and the size goes down for older clusters going near the center, which all just factors into the density calculations. So I think that's about it for this figure. We can move real quick to the last one, but we kind of covered the last one, and it's really interconnected between like figures 7, 8, and 9 are really interconnected. So I basically just explained most of it.
Yeah.
Except like panels B and D, we can look at those real quick. So B you actually saw earlier. These are just ages. superimposed on the galaxy, again, just so you could see where the old and super young clusters are located. So B is not super interesting, but D are the densities that we just looked at, right?
Yes.
And again, the blue values here mean low densities, and the red color means a high density. So just basically the bright red clusters are really dense, and the bright blue clusters are less dense. And you can kind of sort of see that there are definitely more red points near the center than in the outskirts of the galaxy, which just shows the same thing that we saw in the previous figure. So yeah, that's basically it. Those are basically the two most interesting findings in this paper that we highlighted.
Very good.
Have a drink real quick.
Very good. So let me ask then. So where do we go from here? Given what you published in this article, and as you referenced several times in your previous articles, do you try a different neural network technique on M83? Are there other techniques for M83, or can you try this on other nearby galaxies, or plans for that? So where do we go from here?
Well, I think that convolutional neural networks are definitely the right step forward for like this task of cluster search and parameter inference. So one thing I'm definitely looking forward to seeing is basically them being applied to a whole bunch of different galaxies, not just the two that I tried, but everything else as well. So that's like one of the most obvious things that I was going to say, but more from a network training perspective, the thing that would improve the results the most and make it much easier to apply, in my opinion, would be figuring out some way to deal with backgrounds when training the network. Because I mentioned at least several times that there's a lot of problems with the backgrounds because they're not really true negatives. They always contain real clusters. Yeah. And this is a problem not only when testing the network, but also when training the network, because you have to show him the network examples of what's a cluster, what's not a cluster. So you end up showing him a whole bunch of mock clusters, which is fine. We can draw mock clusters pretty well. But for backgrounds, what we end up doing is showing a bunch of backgrounds cut out from real galaxies. And as I said, those contain clusters and all that stuff. So finding a reliable way to model these backgrounds would be like the main thing that would help improve results for all of these techniques, and not only for star clusters. And of course, modeling backgrounds is like much harder than modeling clusters.
Yeah. Okay. Are you aware of any observational efforts to follow up on some of these candidates?
Like these candidates that were found here?
Yeah.
Well, definitely not. The paper came out about a month ago. So I hope people takes a look at this, more people that is, but it's a little bit early for it. Yeah. Okay.
Okay. Very cool. Nice work. I enjoyed this article. I enjoyed the analysis that went with it. So thank you very much for walking us through the article.
Welcome. It was fun.
All right, Jonas, thank you so much. And thank you, everyone. We'll see you on the next one. Bye-bye.